Okay, so how are we going to address the noisy samples problem, the noisy capital G samples issue that will usually, or in many cases, results in slow learning? So we're going to do something that we did previously in many times. We'll just use an approximation for the state value, for the expected G, right? Instead of relying on samples, we'll just try to learn the expected value. For instance, we can use bootstrapping approaches, but the main idea here is that instead of using one sample value, we'll try to rely on an estimation of the expected G, right? So not one sample, rely on one noisy sample, but try to somehow learn the expected, the Q value or the state value. But in this case, in order to use the policy gradient theorem, actually we need to train the Q values. We've seen that before, by the way. If you go back to our previous lecture, you'll see that originally we started by relying on Q values. However, we said that we don't have those, and we replaced those with capital G value or capital G sample. And now we'll take the step back. We'll try to reintroduce the Q value and try to approximate it. And this is something that we've done before in value-based approaches. So let's define a new estimator. This will be our critic. And our new estimator is an estimator for the Q value. It's a function approximator. And we'll try to approximate the true Q values. So we'll swap the capital G with our Q estimation. How can we train Q hat? So we've seen several approaches before. We've seen several approaches to train a state value or action value approximator, and either use Monte Carlo updates. However, these are usually high variance and they are episodic. They require us to finish a full episode. Another approach that we already seen before would be to use bootstrapping. For instance, do basic Q learning, or use a legibility tracer or n-step bootstrapping. That should also work fine. However, these types of updates would be lower variance, but however, they will introduce bias. We discussed that before. But in many cases, the introduction of bias is worthwhile just to get the reduction in variance, to get the better approximated value. What would be the critic's duties? It will need to approximate the state or action or advantage values that would be used inside the policy gradient, within the policy gradient approximation, policy gradient theorem, to approximate the policy gradient. They can be trained via using bootstrapping, but not necessarily, right? We can use a Monte Carlo approach, although then it won't be similar, but it can be about similar as just sampling capital GT. It won't give us a lot beyond that. So probably we would like to use bootstrapping. And its duties is to criticize the action chosen by the actor. So it will be something like our baseline function. And then we would adjust the actor's policy gradient according to this value. Okay, so what would be the critic's duties, the value approximator duties? First of all, it will need to approximate either the state or an action or an advantage value. Right, the advantage value, we've seen that before. It's just the difference between the action value given a specific action, right here, minus the current state value. It is the policy-based state value. And so this tells us the advantage of taking a specific action over the current policy. The critique is usually trained using bootstrapping. Else there's not much advantage to it over the basic Monte Carlo approach. It criticizes the action chosen by the actor. Does so by adjusting the actor's policy or the actor's gradient, the actor's policy gradient. So we've seen something similar before. We've seen reinforced plus state value as a baseline, and we've seen the pseudocode in the previous lecture. So is this an actor critique framework? So it might be confusing because we are both training a state value approximator and the policy approximation, but this is not considered an actor critique framework because the state value function is used only as a baseline and not as a critique for the chosen action. That is, we still rely on full samples from the environment. We don't use the critique to define the full, let's say, benefit of using a specific action at the current time step. However, so as we discussed before, once we rely on state values or action values or any kind of value approximation to decide or to criticize, to decide if a specific action at a specific time step was beneficial or not, if we rely on approximation, then we introduce bias. And we must introduce bias. We saw the birds example where in some cases it must be the case that that bias can be very counterproductive, lead us to divergence in learning. But in most cases, the bias introduced, in many cases, the bias introduced through bootstrapping is worthwhile because it reduces variance and accelerates learning. So in many cases, you'll see that using an approximation for both the G value or for the entire advantage function here is actually worthwhile in sample efficiency. It will cause faster training, result in faster training. So indeed, let's discuss the benefits from a critique. We saw previously that reinforced with a baseline is unbiased, right? In some cases with a linear state value approximator, and when B is not a function of A, so we had some restrictions on the choice of the approximator and how we set the baseline function. However, reinforce is guaranteed to converge asymptotically to a local optimum. Okay, we still have a very non-convex space, so it will converge somewhere, not necessarily the global optimal, but it is guaranteed to asymptotically, at the limit, converge to at least a local optimum. This is not normally the case, right? For if you don't use if you use a non-linear state value approximation, we've seen cases previously where it might result in divergence of learning. So you can't guarantee convergence. In the general case, however, in most cases in many cases we see that it does converge nicely, even if we don't use a linear approximator. However, like all Monte Carlo methods, it tends to learn slowly, right? Because it produces estimates of high variance, so the gradients might be very noisy. So over many samples, we are guaranteed to have the correct direction of the updates, but we commonly need many samples. So training might be very slowly. And at the end of the day, it's also not suitable for online or continuing problems. Why is that?
Not sure.
Because it's episodic, it requires a full episode, right? In order to have the G sample, the capital G sample, you have to have a full episode. And temporal difference method can eliminate these inconveniences. So let's define a critique that is not based on a full sample, on a capital G, but a critique that is updated over time using temporal difference, bootstrapping methods. And now we have something that can work online, can do our updates every step, and we are not requiring to finish a full episode. In order to gain the TD advantages, in the case of policy gradient methods, we use actor critique methods. So it's important to note that actor critique algorithms can be thought of as a derivative of policy iteration. If we go way back, right, we discussed policy iteration for offline methods at the beginning of the course. And as you remember, these methods alternate between policy evaluation. So you start with some policy, and then you do on-policy evaluation. You try to learn the state values or the Q values for that specific policy. And then you do a policy improvement step. Given these values, how can we improve the policy? And here's a better policy. We show that a better policy must be obtained as we're converged. We obtain a better policy, and then we repeat the process. We evaluate the new policy and come up with a better policy. So we've seen that before. However, there's an important difference between the offline policy iteration algorithm that we've seen before and the actor critique methods. So actor critique methods are, as I said initially, they are considered policy iteration, an extension of policy iteration methods, but usually in the actor critique methods, we don't do a full policy evaluation step and then a policy improvement step, but we combine both of these because of the large state spaces. So going back to your implementation of a policy iteration for offline policy iteration, remember that you normally did that on fairly small state spaces. I think in the home assignment it's mainly on grid cell environments. However, once we go to very, very large scale problems, it becomes impractical to run either of these steps to convergence, either the policy evaluation or the policy improvement. Instead, the value function and policy are optimized jointly. So we optimize both at each step. So at each step we update our policy evaluation and we also change our policy. If we do it in small enough steps, it's usually fine. And I know that it sounds a bit hand-wavy at the moment, but later on I'll actually show you some proofs or a specific case where this is fine. We do both of them at each time, and we're still guaranteed to see monotonic improvement in our policy. These are known as trust region policy optimization methods. We'll discuss that in our next lecture. But going back to our actor critique methods, in these methods, the policy is referred to as the actor and the value function as the critique, as you might have guessed by now.